called a tuned amplifier. Reason is it amplifies the signal or boosts the signal at a center frequency with a spread or with a bandwidth which is very small around the center frequency. So if the center frequency is omega 0, when I say frequency, I actually mean the angular frequency. Frequency and angular frequency are related by 2 pi, by a factor of 2 pi. Omega is the angular frequency, omega is equal to 2 pi f. F is the frequency. So if the center frequency is omega 0, then on each side of the center frequency, there will be a spread of frequency over which amplification will occur. On left side, from omega 0 towards left side, it goes by a factor 1 by 2 RPC. Towards the right side also, it goes by a factor of 1 by 2 RPC. So if 1 by RPC is very small, which is the bandwidth is very small, then we call it a tuned amplifier tuned to omega 0. Otherwise, if it is large, then we call it a wideband amplifier. So we were discussing about the narrowband amplifier or tuned amplifier. The equivalent circuit of the tuned amplifier, the RLC equivalent circuit of the tuned amplifier is shown on the left side. If you look at the figure, the left side shows the equivalent circuit. So in the equivalent circuit, what it shows is it is a parallel RLC circuit. The resistance is Rp, inductance Lp, and capacitance Cp. This is a parallel RLC circuit, and it is connected to a source with a current source I in, which is equal to Gm into V in. Gm is the transconductance, V in is the input voltage. And so you can also say that this source, current source, is connected to a tank circuit, and the impedance of the tank circuit is Z tank. Now, what will be the gain of the tank circuit, or what will be the gain of the amplifier? That we have to find out. How do you find out the gain? Gain we find out by calculating or finding the output voltage and dividing it by the input voltage. That gives us the the voltage gain. How to find out voltage? Output voltage we will find out across any of the elements. Since all the three elements are connected in parallel, it is a tank circuit. So we will consider the output voltage across the resistor. It is same as considering the output voltage across the capacitor or across the inductor. We will consider it across the resistor. Now gain will be maximum when this circuit is resonating. So at its resonance, the gain will be maximum. Because what happens at the resonance? At the resonance, there will be no energy storage. Energy in the capacitor and energy in the inductor, they cancel each other, and complete energy is consumed by the resistor. Therefore, that gives you the maximum gain. So at the resonance, there will be no energy across Cp or Lp, which means we can find out the voltage across Rp. Now what will be the voltage across Rp? Voltage across Rp is equal to I into Rp, current into resistance is the voltage. So V out is equal to I in into RP. Why I in? If it is a parallel circuit, I should get divided between C, L and R. But we are saying that it is I in through RP. Why it will be I in? The reason is it is at resonance. When it is at resonance, the current through LP and CP, they will cancel. So only current will be through RP. So total current will go through the resistance. Therefore, the current through RP is I in. At the resonance, remember, not always, only at the resonance. So at the resonance, the current through RP is I in. So V out will be RP into I in, which is equal to RP into GM into V in. So V out by V in is equal to RP into GM. So RP into GM is the maximum gain. So now look at the figure on the right hand side. The maximum gain is GM into RP. So on the y-axis, the gain is plotted. V out by V in is plotted on the y-axis, that is on the y-axis. Along the x-axis is the frequency or angular frequency. So maximum gain will be GM into RP. That will occur at the frequency of omega 0 being the resonant frequency. And it will remain constant over a small band of frequency, which is 1 by RP into CP. So this we have already seen in the last class. 1 by RP into CP is the band. So now we know what is the gain. Maximum gain is GM into RP, and the bandwidth is 1 upon RP into CP. So gain bandwidth product will be G into VW. G is equal to GM into RP. VW or bandwidth is 1 upon RP into CP. Multiply them, RP will cancel from numerator and denominator. So gain bandwidth product is equal to GM by CP. So this expression is just like the low pass filter, and it is independent upon the center frequency omega 0. This expression does not depend on omega 0. So, but in practice, we require to operate at a frequency which is less than Ft of the device. So, omega 0 has to be less than Ft of the device. That is on the caveat. Now let us consider the Q factor, quality factor or Q. So, we consider the issue of Q or issue of quality factor. The figure that you can see is the same figure as we have seen in the previous slide. So we need not worry about the figure, the explanation of figure. Now let us define what is Q factor Q. By definition, you know Q is equal to omega into energy stored by average power dissipated, or power stored by average power dissipated, or energy stored by average energy dissipated. So that is the definition of Q. Now at resonance, when we are operating at omega 0, which is much less than Ft, at that point Q is equal to Rp by omega 0 into Lp. If you consider the RLC circuit, tank RLC circuit, for the tank RLC circuit, Q is equal to Rp by omega 0 Lp when we consider the inductance, and that is equal to omega 0 into Rp into Cp when we consider the capacitance. So that is what is Q. Now if you compare these two, then Q is equal to omega 0 into Rp into Cp, that is equal to omega 0 divided by 1 upon Rp into Cp. As you know, X is equal to 1 upon 1 by X. So Rp into Cp is equal to 1 upon Rp into Cp. So that is what we are writing. So omega 0 by 1 upon Rp into Cp. Now 1 upon Rp into Cp is the bandwidth, and therefore Q is equal to omega 0 by bandwidth. So from this we find out that Q factor or quality factor is center frequency by bandwidth. So there are two definitions. First definition is Q is equal to omega into energy stored by average dissipated energy, that is equal to, you can find out as at resonance, it is omega 0 by the bandwidth. Now when we are going to design a tuned amplifier using these principles that we have discussed, using these concepts, how we are going to design the amplifier. There are three parameters which are important for designing the parameter. First is gain of the amplifier. Gain is Gm into Rp. Then the center frequency, which is omega 0. Last parameter is the Q, which is omega 0 by bandwidth, or omega 0 into Rp into Cp. Now if we have a high Q, then what will happen? If we have high Q, benefit is it will allow achieving high gain. With high Q you can definitely achieve high gain with low power. That is a major advantage of having high Q. But at the same time there is a problem. It makes the circuit sensitive to the process and temperature variation. So when we are designing the circuit, the process of designing the circuit is very typical, and that will affect the circuit performance. Circuit is sensitive to the design process. For high Q, if you have high Q, you are designing a high Q circuit. Also temperature. Temperature variation affects the quality factor. Then quality factor will affect, if quality factor is affected, means omega 0 or bandwidth is affected. So those are the problems. Now what are the other issues? One issue is the gate to drain capacitance that can cause undesired oscillation. When we have a gate to drain capacitance, the equivalent circuit that we saw for the amplifier neglects these things, this gate to drain capacitance, etc., or gate to source capacitance. These are neglected. Now suppose they are present, they will be present, definitely they will be present. Now when they are present, they cause undesired oscillation. Why they will cause undesired oscillation? The reason is simple. Oscillation, when you have oscillation, frequency, frequency is 1 upon LC. Now if you change LC because of gate to drain capacitance, if there is a change in the capacitance, total capacitance, then the oscillation will change or the frequency will change. Now look at the circuit. Look at the circuit of the amplifier, narrowband amplifier circuit. We are looking at the narrowband amplifier circuit. And the circuit we have discussed earlier. Only thing is here we are looking at this gate to drain capacitance is there, gate to source capacitance is there. These two are there. And looking at the input impedance from the input side. So if you are giving the signal as input, V in is the input signal. So from that side, look to the amplifier or the transistor. The input signal, input impedance is Zin. If the input impedance is Zin, then the admittance will be Yin. It will depend on the frequency. So Yin is a function of omega, which is equal to J omega CGS or J omega into capacitance between gate and source plus J omega into capacitance between gate and drain into 1 minus AV. This expression we have already seen. Okay, so we are going to use this expression when CGS and CGD are dominant. Now here AB is the gain. Gain is equal to minus GM into Z tank. Z tank is the impedance of the tank circuit. So AV is equal to minus GM into Z tank. In the previous slide, we have also seen that AV is equal to GM into RP. Now RP is replaced here by minus GM into Z tank. At frequencies which are below resonance, at those frequencies, the tank is more inductive. Above resonance, the tank is more capacitive. So the tank circuit behaves like an inductor below resonance, behaves like an capacitor above resonance. So below resonance, AV is equal to minus GM into J omega L. Why J omega L? Because the tank circuit behaves like an inductor. So Z is equal to J omega L. So AV is approximately equal to minus GM into J omega L. So using this value, we can find out what is Y in. Y in or input admittance is equal to J omega S into capacitance between gate source capacitance. That remains as it is, plus J omega into capacitance between gate and drain, whole into 1 minus AB. AB expression we have found out. So if you put that, then it becomes 1 plus GM into J omega L. Now expand that. If you expand that, then input admittance is equal to J omega into capacitance of gate source capacitance plus J omega gate drain capacitance minus omega square GM into gate drain capacitance into L. Now if you look at this expression, we have a omega square term which is negative. Now omega square term, if you consider omega square term to be negative, which means Y in can be negative. A real part of Y in is negative, which gives you a negative resistance. Imaginary part, forget the image. Imaginary part is capacitive. Real part is the resistive part. The resistive part is negative. So admittance is negative, therefore resistance is also negative. Now suppose we are going to use cascode device to remove the impact of CGD. In the expression for Y in is equal to J omega CGS plus J omega CGD into 1 minus AV. And now we want to remove or minimize the impact of CGD. So how to do that? To do that, we are going to use a cascoded structure or cascoded amplifier. So we have M1 is our main transistor. Then we have M2 which is in red. So that is the second transistor. Second transistor will not have any input, it will have only bias. The input will be given to the first transistor. Otherwise, this circuit is same as the circuit that we saw in the previous slide. Now here, in this case, once you go for cascoding, then AV is equal to minus GM1 into 1 by GM2. Minus GM1 into 1 by GM2. That also we have seen when we discussed first time the cascoding. So AV is equal to minus GM1 into 1 by GM2. So how does that come? For if you don't have cascoding, it is GM into RP. When you have cascoding, it is GM into RP into 1 by GM into RP. So RP will cancel out. GM For first one it is GM1, for the second transistor it is GM2, so they will be there. So AB is equal to minus GM1 into 1 by GM2. So at the frequencies above and below resonance, at resonance these C terms won't be there. So frequencies above and below resonance, for AB if you put minus GM1 into 1 by GM2, then Y in is equal to J omega CGS plus J omega CGD into 1 plus GM1 by GM2. Now if you look at both these terms, there is no resistive term. Both these terms are capacitive because it is J omega into something, and therefore that part is capacitance part, which means this circuit using the capacitance, this circuit becomes purely capacitive. So Y in now becomes purely capacitive, so Z in also will be purely capacitive. Okay. Now we want to neutralize the tuned amplifier. To neutralization for the broadband amplifier, remember the neutralization of the broadband amplifier, what we did is we used one op amp which is giving us 180 degree out of phase output. Input is equal to output, or we used an op amp of unit gain but 180 degree out of phase, 180 degree phase difference. So here also we will do that, use an op amp of unit gain with 180 degree phase difference. Now and then for matching, what we will do is we will use a neutralization capacitance which is Cn. Cn is a neutralization capacitance which will match. So therefore the circuit looks like this. The circuit now only changes the red portion. So the circuit looks like this. So for a narrowband amplifier or tuned amplifier, the inverting signal that can be generated by the tapped transformer, or that we have used here. So just use a tapped transformer and generate on the inverting signal. So either use a tapped transformer or use this circuit. We are using this circuit here. Now on that circuit is equivalent to using a tapped transformer. So here we are using a tapped transformer, so we have just replaced the unit gain amplifier by a tapped transformer. So the tapped transformer is an inductor LT and it is tapped at its center. So and this is a tapped transformer. Using this, only the problem with this is once you use inductor, then it requires more area, more real space. Real estate is more. So problem is area and quality of on-chip transformer is affected. Then neutralization capacitance Cn must be matched to CGD. This matching is a must in this case for neutralization using tapped transformer. These are the problems. Now what we can do is we can do the neutralization using differentiation. So use the difference principle to neutralize for a narrowband amplifier. So we will discuss the differential neutralization for narrowband amplifier. Same principle, remember the difference amplifier or differential amplifier that we discussed for the broadband amplifier. Use the same principle. So same principle as differential neutralization in broadband amplifier. The issue left is matching of Cn to CGD. Now how to do that? How to find out a Cn which will match CGD? Mostly you will use for Cn a CMOS transistor, or you can use a lateral metal capacitor for Cn. These are the two things that we can use. Mostly preferred is CMOS transistor. Because lateral metal capacitor, once you put lateral metal capacitor, those capacitors may have resistance. So resistor will come into play. To avoid that, CMOS transistor is the best choice. Then we will consider something called the super regenerative amplifier. Regeneration is there. Look at this circuit. In this circuit, we are giving an input Vin through a switch, which is switching with a frequency Fc, that is called quenching. So the switch is switching with a frequency Fc, and the switch is connected to an RC circuit. So C, then R is negative resistance. We have seen the negative resistance. When we get negative resistance, that we have just seen. Then it goes to Fc, SH. Then we get the V output. Now, in this V output voltage is equal to input voltage into exponential T by RC. So output voltage, their time dependent output voltage is V in 0. So at the time 0, T is equal to 0, whatever is the voltage, that whatever is the input voltage, that into exponential T by RC. Now V in is sampled at the rate Fc because of the switching. So this is, in practice, the implementation of Fc can be dependent on the input level, whether you require high input or low input. High input is, you can say that Fc is on, low input or zero input Fc is off. So in practice, the implementation is Fc can be input level dependent, high or low. Now the sampled output voltage, sampling time is capital T is equal to 1 by Fc. So sampled output voltage for small t, just replace capital T. So V output capital T is equal to V in 0 exponential capital T by RC, where capital T is equal to 1 by Fc. This principle, super regenerative amplifier principle, can be used for both broadband amplifier and narrowband amplifier or tuned amplifier. I will do simple analysis either for broadband or narrowband amplifier. Now let us find out what is the gain. V out is equal to V in into exponential T upon RC. So AV or gain is equal to V out by V in, that is equal to exponential T upon RC. Then we know Nyquist theorem. Nyquist theorem say that when you are sampling or when you are switching, sampling means you are taking samples of the signal. In this case, samples of the input signal V in. If we are taking samples of the input signal V in, then those samples should be taken at such a rate that it satisfies this condition. The sampling frequency Fc should be greater than twice the bandwidth, or bandwidth should be less than Fc by 2, that you can say bandwidth should be less than 1 upon 2t. So maximum bandwidth into log of AV is equal to exponential T by RC. So if you take log on both sides, so log natural of AV is equal to T by RC. Maximum bandwidth is 1 by 2T. So maximum bandwidth into log of AV is equal to 1 by 2T into T by RC, that is equal to 1 by 2 RC. Therefore, this shows that the bandwidth can be traded only logarithmically with gain. Maximum bandwidth, the product of maximum bandwidth and log AV is equal to 1 by 2 RC. So this shows that it trades bandwidth only logarithmically with the gain. Now let us look at an example, narrowband example. This is a circuit, BJT circuit using BJT. RB is the DC bias resistor. LC and C1 are tuning LC circuit, so tune circuit. Then C2 is a positive feedback to the amplifier. LE is the RF choke, radio frequency choke, which is in fact a large inductance. When the RF amplitude becomes large, look at this, when the RF amplitude becomes large, it is rectified at the emitter of the Q1. So at the Q1, it will be rectified. RF amplitude is large, it will be rectified. You have a rectifying circuit, it will be rectified at the emitter of Q1. Now if it is rectified at the emitter of Q1, because of rectification, the RF will be converted to DC. So this will raise the DC potential at the emitter of Q1. So the DC potential is increased at the emitter of Q1, which means the emitter base junction is, the voltage across the emitter base junction is increased. So that will switch off the Q1, because that is reverse bias, that will switch off the Q1. So Q1 will be switched off. On the other hand, if RF oscillation dies, if it is switched off, then there will be no amplification. So ultimately RF oscillation will die. When RF oscillation is dies or it is quenched, then what will happen? There will be no rectification. So DC potential at the emitter of Q1 is returning back. So you will get back the DC potential at the emitter of Q1. So once you get back the DC potential, then the amplitude of oscillation will grow. So that will grow again due to positive feedback. So the process will continue. So it will grow. Once it grows, then you will, the peak will be coming back to this Q1. Then it will be rectified. Then it will be switched off. Once it is switched off, then no rectification. So you will again get this oscillation, or you will get the DC potential will come down. So amplitude of oscillation will grow. So the oscillation ultimately will grow and decay. That is what is oscillation. Now let us consider a simple active real impedance generator. So in this, what we are doing is we are using an amplifier whose voltage gain is AV, which depends on frequency. So AV is dependent on S, AVS. AVS is equal to minus A0 exponential minus JP, P being the phase. So input and output, the phase difference is 5. Now on this, if you look at this circuit, the input admittance of the circuit Yin is equal to J omega CF. CF is the feedback capacitor. So J omega CF into 1 minus AV. This you are expected to know from your op-amp circuit. If you have not read it, read it. Op-amp circuit is simple. So Yin is equal to J omega CF into 1 minus AV. Actually, this is Yin is equal to 1 by YF. So YF is equal to J omega CF. Yin is equal to YF into 1 minus AV. YF is equal to J omega CF. So that you can write as J omega CF into 1, then AV is equal to minus A0 exponential minus AV. So put that. So if you put that j omega Cf into 1 plus A0 exponential minus Jp. Now what we can do is, we will separate the real part and the imaginary part. Imaginary part will be j omega Cf into 1 plus A0 cos phi. So imaginary part is capacitive in nature, plus the real part is A0 omega Cf into sin phi, which is resistive. So we have got a resistive component in the active real impedance generator. So if you use that, there will get a resistive component. This principle, now apply this principle to the impedance matching network. So for impedance matching, we will use that principle. So what we will get here is, we will see that it is advantageous to make Zin real without using any resistor, using the principle that we just saw. So we can make Zin real without using any resistor. Zin can be made real. So how to do that? Look at the above circuit. Use the equivalent circuit of the CMOS. So the equivalent circuit, if you use the equivalent circuit for the CMOS, and for the circuit we will see this, the equivalent circuit is given below. At the bottom the equivalent circuit is given. Look at the equivalent circuit. Equivalent circuit is I test, is the test current that you are giving, and that goes through CGS. Across CGS voltage is VGS, then that is connected to LS, and to the transistor as a gain. So transconductance is GM, VGS is the current source. So GM into VGS, that gives you the current source, the equivalent current source for the transistor. CMOS is a current dependent device, So voltage dependent current device is a FET, CMOS FET. So this is the equivalent circuit. Now from this circuit you can find out what is V test. Simple Kirchhoff's law use, simple Kirchhoff's law, Ohm's law, etc. Find out what is V test. V test is equal to I test into 1 upon S into CGS plus S into LS, that into 1 plus GM into 1 upon S CGS. So then simplify this. Once you simplify this, you will find Zin S. What is Zin S? Zin is equal to V test by I test. So find out what is V test by I test, that is Zin S. Simple algebraic simplification will give you Zin S is equal to 1 by S CGS plus S LS plus GM by CGS into LS. So this shows that Zin is in this form. This is like a series resonant circuit. Now use a series inductor to tune to the resonant frequency in the circuit. Use a series inductor. If you use a series inductor, then instead of looking at Zin exactly at the transistor, you will look at the Zin through the inductor, series inductor Lg. So red one is the added part. Now calculate the input impedance with the added inductor, the inductor that we have added. So use that added inductor. So for that, the impedance will be same as the previous case, only we will add a term S into Lg. So that term is added. So S into LS now becomes S into LS plus Lg. So that we can do. In order to choose the resonant frequency and input resistance separately, you will do this. Often we will require pure resistive component at frequency omega 0. So to do that, choose Lg such that the resonant frequency omega 0, we want at the resonant frequency omega 0, you will require 1 upon root over of Ls plus Lg into Cgs is equal to omega 0. That is the resonance condition. Omega is equal to 1 by Lc. So if that condition is satisfied, then you will get a pure resistive component at the frequency, resonant frequency. Any RLC circuit which satisfy the condition omega 0 is equal to 1 by root over of Lc resonates at that frequency, and at the resonance it has only resistive component, other components are neutralized automatically. So we'll finally consider the narrowband alternative to LC. On-chip inductors take up considerable die area and have relatively poor Q. What are the alternatives for on-chip inductors? Use quarter wavelength transmission line for the resonator. That is one alternative. Earlier we have seen that if you use a quarter wavelength line with shorted load, that behaves much like a parallel LC circuit, while with open load it behaves like a series LC circuit. Only problem with this is the dimension. Suppose you are using a 900 MHz mobile phone. So the frequency is 900 MHz, or that lambda by 4 in free space is 3.25 inch, which is quite large compared to the mobile phone. So for 3.25 inch you cannot have within the circuit this large. With high permittivity dielectric material or ceramic materials, the size can be reduced to reasonable dimension. Usually you use epsilon r is equal to 10. The length of the waveguide is about an inch. That is also quite large. Different configurations of filters can be built by combining sections of series and parallel equivalents. That is possible. This is more appropriate if you choose frequencies over 1 GHz. Over 1 GHz size will be smaller. So that we will take a break here. After the lunch we will discuss about the noise. So here we will stop. We will discuss about noise after lunch. After lunch we will discuss about what is noise, what are the source of noise in an amplifier, because finally we will discuss about low noise amplifier. Attendance nature.